今天要开始进入下一个章节，随时间会随时间变化的场。之前we talk about electrostatics and then magnetostatics. Now, if the field changes with time, then you're going to see that the electric field and magnetic field are going to couple together. And in fact, you have seen this in the last chapter. When we have a time-varying magnetic field, 你有一个随时间变化的场，这个场的时候呢，这个磁场 ，you can induce a voltage across a circuit loop, and this is the electromagnetic force coming from the variation of the magnetic flux over time. 那在这里不要忘了，这个前面有一个负号，这是 Lenz's law. It tells you that the change of the induced voltage is going to oppose the change of the magnetic field. Okay, and 所以这个是之后会告诉你，这个式子整个有一个称呼叫做Faraday's law of induction. Okay, 所以呢，随时间变化磁场会产生一个电压出来，这个电压基本上 is an integration of the electric field over a loop. OK， 那在这里你必须小心，就是on the right hand side, this integration magnetic flux is a magnetic field over some surface, but the differentiation right here is the differentiation is a total differentiation over time. OK, now when you look at this formula for the magnetic flux, it's a B dot ds, but you'll be doing the total differentiation of this magnetic flux over time. So on the right hand side, this is a function of B and also surface. Or specifically, this is a function of B and some dimension. So when you do this total differentiation, you have to consider that this B could be a function of time. This position, the area, okay, the area could be a function of time as well. Okay, this R could be a function of time as well. So you have to do the differentiation on B and also S, but not just on B. So this equation, you have to do two differentiation. VEMF equal to minus. This is a differentiation, and then B dot ds. You have two equations, 1 plus 2. One is the differentiation. One is the differentiation of the field with respect to time. So this term is easy. This term is you just take the differentiation of B with respect to time, and then do a surface integration. But the second term is a little bit difficult because you have to take a differentiation of the area with respect to time. And this belongs to some mathematical skill, some mathematical derivation. Okay, but because we are not mathematicians, 我们不是数学家，所以呢 we argue from some physical point of view and try to understand this term. Okay, so if I have a loop, circuit loop, and bounding some area, so this is area, And now if we allow some magnetic flux going to this flux, and this B is a function of time. Suppose that this circuit loop does not move. 它不移动. If it does not move, then we only have this this term. Okay, and so let me give you one a sense of it. If you have a circuit loop like this, and then this circuit loop does not move, and you have a magnetic field, magnetic flux going through this loop, and it varies time, so this calculation is very easy. Comes from just use this formula to do the calculation. Okay, and you can have an equivalent circuit like this. Just replace this as, with the voltage source, because this is a generator. Okay, and the voltage source is described by this equation. Okay, any question about this? 到目前为止，如何用这个 Faraday's laws of induction? 没问题 right? This is very simple, straightforward sense of about the induced voltage due to the time varying field. Okay, now if we have a second situation that this area varying with time, how could it happen? For example, if I have a resistor right here, and then I make a sliding bar. Okay, suppose this there's a magnetic field, there's a B field, go into this ball, and then I make a sliding bar. This sliding bar is conducting, is a piece of conducting material, and just move it. Okay, so the area, the integration of this area changes with time. Right? 我如果移动这个 sliding bar 的话 with a velocity of u, the area of this circuit loop is going to change with time. Then you have to think about how to do differentiation of this area with respect to time, because this S now is going to be a function of time. Okay, so mathematically you need to deal with the a differentiation of this area with respect to time, but physically let's see how this current is going to flow. 为什么它的电流要运动要开始跑出来？这个面积在变，为什么这个电流会跑出来？那它是一个能量 ，so we can argue it from conservation of energy. The current comes from, well, we don't know yet if the current is going this way or this way. Okay, we don't know yet. But the current must come from some energy. Okay, that is the kinetic energy of this sliding bar. 所以在这里呢，你知道里头有电荷。Inside piece of wire, there's charge inside. Okay. So given the charge inside, there's a force pushing this charge according to this Lorentz force equation. So when I slide this, there's a charge inside. So the charge experiences a magnetic force this big. 所以呢，电荷在里头会被拉动，所以我们可以找出它电流方向了。Okay. According to this, this is U cross B. Now the charge move, the sliding bar move in this direction. So if I use my 5 fingers, point along the U direction, and I move my 4 fingers toward the B direction into the ball, then my current is going to move in this direction. Right, so now I figure out the current has to be along this direction, but the electron is going to move down because the electron charge has a minus sign. So electron is going to electron is going to move down. All right, but current is going to move up. So this is a physical origin of the current, induced current, due to this variation of the magnetic flux. And basically it's a time variation of the area. Okay, so there's a cutting of the magnetic flux due to this sliding bar. So we call this, there's a voltage induced across this loop. Okay, and we call this flux cutting EMF, electromagnetic force, or motional EMF. 所以这个它产生这个电流的物理机制了解 ，right? Because of this Lorentz force. Then let's ask how big this EMF is. How big this voltage you can induce given moving of the wire. Well, this force push electrons. So equivalently, there's an electric field that move this electron. This equivalent field will give the charge a force equal to this big. Right, to an electron. 这个在动的这个电荷呢，在被推动这个电荷，它不会知道这个力怎么来的，所以呢，它觉得自己被推，所以呢，被一个电场推。So this electric field is going to be equal to U cross B. So now you have an equivalent field equal to U cross B. And given the electric field, you know how to write down the voltage. Basically, a voltage is just a cross-loop integration of the electric field over the whole loop. 所以呢，很直接、很简单的一个结果，完全从物理上的这个观点上头来看。所以这第二项我们知道怎么写了。第二项呢会等于a cross loop integration of U cross B dot with dl. And this comes from the flux cutting EMF. Okay, and for the first term, there's no moving wire. The area, integration area, is nothing to do with time. And this term is called transformer EMF. Okay, so for this, the Faraday's induction law given by the total differentiation of the magnetic flux with respect to time consists of two terms. The first term, there's a minus sign in front of it, okay? And you take a differentiation of the B field first and then integrate the term over the surface. And the second term is associated with the moving of the area or moving of the dimension. 所以有两项在那个地方，有没有问题？所以我们来看一下这个Faraday's law of electromagnetic induction. Basically, the governing equation is like this, and this is the total differentiation of these two variables, B and ds. And this is only valid for one loop. If you have many loops, then you have to do a differentiation for the magnetic linkage. Okay. So be careful that in fact there's n in front of this expression. And given this configuration, okay, you only have to take differentiation for the B field with respect to time. Okay, because for this configuration, the dimension of this loop does not change over time. So this calculation is very simple. OK， 那在这里呢，我刚刚帮各位算出有一个这个 flux cutting EMF given by this expression. In case the area of the flux you calculate is a function of time. 所以这些都已经告诉你们。所以呢，这个 the complete expression for the Faraday's law of induction is given by this expression, consisting of two terms. One is that you do a partial differentiation of the B field with respect to time, and then you do this the flux cutting EMF. 所以这个里头的物理意义很清楚 ，right， 很清楚。所以我们来看一个例子。这个例子呢，其实就是发电机。一般的发电机里头有永久磁铁，有一个永久磁铁，然后呢，在这里头呢，有这个一个导线圈是类似这种样子，然后呢，这个导线呢，这里有一个轴 ，so you can rotate it。所以这个磁场呢，有固定的磁场方向 from N to S is a permanent magnet, and then this current loop would rotate inside. This mechanical driver could be from water falling from somewhere really high, from some high point to low point, and push this current loop to rotate. 当它在转的时候呢，in a moment you're going to see that there will be a current flowing in this loop to generate electricity. 会产生电流出来。OK， 那我们来算这个，产生的 EMF 可以多大 ？OK， 那在这里呢 ，well, if you just start from this expression, you immediately see that there's no change of the magnetic field over time. So you can just cross out this term. Okay, so you just look for this calculation, and U in this configuration, this U 这个叫做电刷呢，它会旋转 ，OK， and you have to consider the U of the charge. U is the direction of the motion of the charge. 那 you have 4 sections right here. 这个上面、下面跟左边、右边这两段总共有4段的这个这个导线。那这个导线怎么移动呢？基本上它移动的方向呢，就是在转的方向就是 phi 的方向上头 ，right phi 的方向上头。那你若用你的手有4段，这一段有这么4段，然后呢，这个 magnetic field 是这个在这个垂直方向上头 ，OK， and then the motion, for example, for this point, the motion of the wire is say along this direction， 在这个方向上头，这个I have to twist myself, and then 这个你如果做一个 cross product 的话，跟这个 B 的方向做一个 cross product， 那它的这个移动方向呢是在这个电流移动方向是在这个方向上头。Okay, so this means that this section of wire is not going to produce any electricity because the electric current cannot move along this direction. Okay, so only these 2 sections only these two sections of wire can produce electricity. Okay, so basically, the motion of the wire for this section is along phi direction. Say along phi direction. OK， 那这个B field 如果说是这个方向是B0 AZ 好了，这时候呢，你有一个这个cross product， 告诉你说 the current is going to move along this direction, and for the bottom section, the current is going to move this direction. So you have a current flowing over a loop. 那只有这一段跟这一段的贡献 ，OK， 没有这两段的贡献。OK， 你要用手去试试看。那在这种状况之下呢，这个 U 从这里到这里距离是 half of W。所以 U, if I have a rotating, this alpha, the angle here alpha, if this alpha is equal to omega t, then U is going to be equal to 1/2 of W multiplied with omega. Right, R omega 就是它的这个切线速度。那所以在这里呢，你这个式子，你做 integration 基本上就是乘上这个的长度，乘上这个的长度，然后呢有上下两段。So this U is half omega multiply half W multiplied with omega, and then multiply with B, and your integration over this length. But you have two sections. Okay, but don't forget that this is cross product. This cross product is going to give you sine. This U go in this direction. 切线方向，但是呢，你的场呢是在水平的方向上头。So this U normal to this surface. U is normal to this surface, and you have a cross product with B give you sine alpha right here. So you have to multiply with sine alpha, but this alpha is omega t. So this is the complete expression for your induced voltage on this wire. OK， 这个是来自 U 乘上 B， 这个是来自 integration of dl. And this 2 comes from the top section of the wire and the bottom section of the wire. Okay. So this is how you calculate the induced voltage on this current loop. Well, so the EMF is equal to, according to our calculation, this is U cos B dot dl. But we can also calculate this from the original expression, that is B dot ds. We first calculate this B dot ds phi. This B dot ds is equal to B0, the constant magnetic field, integrate over the surface. What is the surface? The surface is H multiplied with W. But this, well, this is S is equal to HW. B, now let's take a scalar that is B0. But the dot product B dot S is going to give you an angle, cosine of the angle between B and S. So you have cosine alpha right here. OK， 这是你从这个从 flux 上头来算，先你整个下去算这个式子的话，你把这个 flux 先算出来。You can do that, all right? And this cosine comes from this dot product. Now, put this expression into this expression. Okay, so the only thing changed with time is this alpha is a function of time, because this alpha is equal to omega t. So now the induced EMF is equal to minus HW. Well, do a differentiation of this cosine alpha with respect to time. So you get minus sine omega t multiplied with omega. Okay, and don't forget that you have B0 in front of it. And you have two minus signs right here, so you make it a plus sign. If you compare this expression with this expression, the two expressions are the same. OK， 所以呢，计算的方法有很多个。你可以從它一剛開始的這個Faraday's induction law 開始 to calculate the magnetic flux first and do a differentiation, or you can start from the calculation of the flux cutting EMF. Any question? 没有问题 ，right？ 这个计算的方法有教你，物理的这个图像也有教你。OK， 我们看一下，我这里有一个 animation。Let me see if it's going to work. Well, basically, the author of this animation fabricate a loop. Oops, a little bit bright. He fabricate a loop of wires, right? And then put some magnet up and down to induce a voltage. So this is very real. The energy comes from the kinetic energy of this person moving the magnet. So now there's a motion. There's no motion of the magnet, and there's no change of the voltage meter. Now you just swing the wire a little bit, and you can see a little bit of voltage induced. You just swing the wire. Why will it happen? 它只是把这个 wire 拿上拿下，然后这里居然会动。OK， 我们再看一次。OK， 他把这个磁铁，这上头有很多的磁铁，他拿上拿下，你可以看到这个电压就产生了。然后呢，他会把它拿开，然后放上去不动它，这里的电压呢就不会动了。Okay, and then later, he just swing this wire, and you can see a little bit of the voltage induced. Although the voltage is quite low, this is millivolts, 这个10的负3次方个伏特，但是呢，你可以看到它在动。这个不是它在动这个 wire 的时候把这个桌子呢震动了 ，no。OK， 这个是来自于就是地球有磁场，地磁造成的这个flux cutting EMF, and then drive the voltmeter. So it's quite interesting. And we just finished the calculation for the flux cutting EMF, and there's a device called called Faraday disk. There's a drawing in your textbook, a Faraday disk. This Faraday disk is an electric generator that produces electricity through this flux cutting EMF. So I also have I also dig out a film for you, so you can sort of feel how a Faraday disk is going to work. Okay, this is the metal frame disk moving with the axis like this, and it moves. And this is a magnet. Okay, so you have a conducting disk on the inside, a moving conducting disk inside a magnet, and this magnet gives you a constant magnetic field. When this moves, you also attach the two wires to this system to produce on this end and this end, and there's a flux cutting EMF induced across the disk. 然后呢 it's going to lead up the bulb. Okay, 你把一个 wire 接到这里，接到这里 because you have flux cutting EMF. So this is a generator that will turn on your light bulb. And we call this Faraday disk. Okay, 这是发电的一些方法。那我也从我的这个实验室里头带了一个东西过来。基本上这个后头这个结构，这个呢后头一个小小结构呢 is similar to this. Okay, there's a magnet, a constant magnetic field inside from a piece of permanent magnet, and then you rotate this to produce electricity, and then turn on an LED underneath of this. So if you rotate this, we have to rotate a little bit hard. If I rotate this, supposedly there will be some EMF produced and to turn on this LED. But if I don't rotate hard enough, you see nothing. But if I do this, you see the generation of electricity to light up the LED. So this is something you can play and get some feeling about the generation of electricity. Okay, so this is kind of cute, so you can play with it. 那通常呢，这个是你在前面有一个大的电风扇，然后你吹它，那它就转，然后呢就会亮。所以 a very nice illustration of a generator. And if you rotate this guy, if you rotate this fan in the opposite direction, you don't get anything. And surely you'll understand why, because an LED is there's a PN junction in it. So if you reverse bias it, there's no current flow through this LED. So if you do this, you don't produce electricity. And if you do it really hard, you can sort of damage this LED, right? Because you have a reverse bias. But if you do this, the current can flow along one direction. Okay. 我昨天本来是到我实验室去拿了一个那个上回助教不是拿那个一个 coil 过来吗？然后呢我想用那个 coil 这个让它产生这个电流给各位看。那我就拿那个黑板，不是有那个小的磁铁，然后那个 coil 这么大，我就把它扔。这个你们到夜市不是有那个小朋友扔那个奖品吗？我也想让你们扔看，结果我的那个 voltmeter 都是伏特级的，它这个 voltmeter 是 millivolt 的，所以 turn out that I did not see anything. But I dig out this small toy for you. So previously we have electrostatics, and we have two postulates. That is curl of E equal to 0, right? And we have divergence of B equal to rho for the electrostatics. And for the magnetostatics, you have curl of H equal to Ga, and divergence of B equal to 0. And this is the Ampere's law. This is Gauss' law. But one thing is missing. One thing is missing. That is a connection. That is a connection between the electric field and the time-varying magnetic field. We have V equal to this integration equal to minus d phi dt. Okay, so something is missing. Something is missing. So we are talking about the differentiation equation. So we are looking into the field at one single point in space. A single point of space does not change with time. 我如果说在空间里头，只看这空间的一点的话，这一点的长度，按照我们这个古典的观点来看的话，这一点长度是不会变的。Okay, so from this equation, and this is going to be b dot ds. Okay, but this expression on the left hand side, you can convert this into curl of E dot ds. Minus sign right here. Through the Stokes theorem. So we have to modify this expression, right? According to this equation, you deduce one important equation, that is curl of E has to be equal to the partial derivative of B with respect to time multiplied with a minus sign, because for this calculation, there's a d dt. For this calculation, you are calculating this magnetic flux at a single point in space. So a single point in space, the dimension of this single point is not going to change with time from the classical point of view. Okay, so 这个式子呢，你很快的可以把它写成 minus partial derivative b with respect to t and dot product with ds. Okay, so compare this with this. You end up having this conclusion. So now you have to modify this equation to minus partial derivative b with respect to t. And we give this equation a name. We call this Faraday's law of induction. OK， 所以呢 Maxwell Equation 这几个式子呢，我们正在改写之中，把它这个随时变的效果呢放进来。OK， but this is not complete yet. This equation also has some difficulty. 为什么呢 ？From charge conservation, this equation in fact is not reasonable. OK， 这个式子并不是那么合理，因为呢，我们两边把它取个这个 divergence curl of H and write it into divergence of J。在数学上 ，divergence of curl has to be equal to 0. But from charge conservation, divergence of J is equal to minus partial derivative of charge density with respect to time. 之前我们说有一个式子叫做 equation of continuity. Divergence of Ga plus time derivative rho with respect to time is equal to 0 because of charge conservation. 一个这个电中性的东西。流进去的这个电荷跟流出来的要一样 ，OK， 这就是你上回算的 Kirchhoff's law of current at one circuit node 的这个式子。OK， 所以呢，这里有问题，左边等于0，右边不等于0，所以这个式子是有问题的。所以在这里呢，我们最好呢，把这个0再加上 divergence of something equal to minus time derivative of rho with respect to time， 必须在这个上头0再加上一项，让它等于右边的这一项。Okay, so we have to modify this expression。了解这个逻辑，来，左边等于0，右边不等于0，那完蛋了，这个式子不能成立。所以你左边这里要再加上一项。但是呢，之前你知道 ，you know that the charge density can you have this expression. So this term in the parentheses, if you do a comparison, the expression in this parenthesis has to be equal to the time derivative of d with respect to time multiplied with the minus sign. OK， 有看出来 ，right？ 所以呢，这个式子，这个负号拿到右手边来，这个式子必须加上一项。这样才完整。Okay, so this now this equation is correct. Physically, what happened is that a time-changing field, electric field, can induce a magnetic field. For this equation, it tells you that a time-varying magnetic field can produce an electric field, and conversely. 反过来 a time-varying electric field can also produce magnetic field. So now, electric field and magnetic field are sort of correlated, connected. They are not independent. 它不是独立的了，它是互相关联在一块。One can generate the other. OK， 所以这边呢，就是整个都联系在一起。这4个式子。The 4 equations right here is called Maxwell Equation. Okay, Maxwell Equations. 很重要的这个4个式子，很漂亮的4个式子，解释了所有的电磁的现象，包括这个狭义相对论。都是从这个式子出来。OK， 那这里头还有几个重要的式子，你学会的这个 from charge conservation, you have divergence J plus 这个 time derivative of volume charge density is equal to 0. And then the Lorentz force equation is also very fundamental. U cross V. OK， 这些都是这个电磁学里头最基本、最重要的式子。And if you have materials, then D is equal to in the linear simple medium, you have this relationship. And in the linear simple medium, if I have magnetic materials, then B is equal to epsilon naught. No, sorry. This is vacuum permeability multiplied with relative permeability and then multiply with H. OK， 所以这些是这个电磁学里头最基本的几个式子，都在这上头，解释所有的电磁现象。All right, any question? 所以我们看一下这个投影片，然后复习一下。So once you put the Faraday's induction law into the 4 equations, then this equation is modified, but it turns out that this equation is not reasonable yet, okay? Because if you take a divergence of this equation, the left-hand side is equal to 0, but the right-hand side is not equal to 0. So this means that you have to add a term to the left-hand side and allow this divergence to be equal to this. But given this Gauss law, the term inside this parenthesis is going to be equal to minus partial derivative of d with respect to t. So if you add this term into the left-hand side, then you modify this Ampere's law. 所以在这里呢，你看到一个现象，就是这两项加在一块，这个是电流。So somehow the variation of the d has a similar property of an electric current. 这一项呢有电流的特性在那个地方。OK， 这一项有电流特性在那个地方，所以在之前 somebody asked me how we define the physical meaning of D。你们之间有个人问我，这个 D 是什么？我们说之前我们知道这是 electric flux density。现在呢，这个 D 又有另一个名称，叫做 displacement。Vector. Okay, because this term is called displacement current. 它有个称呼叫 displacement current. Okay, 为什么它有这个电流的效应呢？ Let me tell you the physics associated with it. Okay, let's think about a capacitor circuit. Okay, think about this capacitor circuit, and there's a current flowing inside. Okay, and if you want to calculate the magnetic field, say somewhere along this path, then I can do an Ampere's law to get this. H.dl has to be equal to the current inside the area defined by this loop. Right, this is an Ampere's law. 那这个里头呢，其实不要忘了这个原来的式子是什么呢？ Curl of H.ds. On the right hand side, this J.ds. So if I define a surface bounded by this loop, and this surface cut through this wire, then this term on the right hand side is not going to be 0. Okay, so let's define this surface like this. 这个 surface 呢，这个电流有穿过这个面，所以右边这个计算不会等于0。OK， 所以呢，这个磁场，这上头的这个磁场可以算出来。But this is not the only way to define the surface. You can define another surface. The surface can be distorted like this. 它可以是一个像带子状的这个面，它并没有说我的这个面呢一定要平的。如果是这样子这个面的话呢，这里你没有真正的 physical current, but you have the same magnetic field. So the calculation become a trouble. The two surfaces with different definition, but having the same boundary loop should give you the same result. But for this surface, there's no physical current going through this surface. So we have to use the displacement current to rescue this this problem, this trouble. Okay, and we'll continue this after 10 minutes.